I'm the Chief Technical Architect at Standard Solutions. We're a Denver-based value-added reseller. And I have this opportunity to talk to you today about Flash. Just a brief overview about this presentation, about what it is and what it isn't. The first part of the presentation, I want to focus on business drivers. And keep in mind, when we talk about business drivers, think about things that are happening like at the very large enterprise level, right? And as I've given this presentation in the past, I've had a lot of people, as we go through this, they'll say, you know what, I'm an SMB. If you are an SMB, keep in mind that whatever is happening at the enterprise will ultimately, that type of technology improvement and innovation eventually gets pushed down into the environment where you're at today. And then the next part of the presentation, we're going to spend time talking about current technology like 2D, NAND, Flash, and 3D. And then we're going to talk about some of the emerging trends that are going on in the market, all of which are happening at a tremendously quick pace. So let's get started. This gentleman needs no introduction, right? Abraham Lincoln, our 16th president, and considered to be one of the top 2 presidents of our country. With these last 5 words in this quote, right? All men are created equal. He set the course for our nation during the Civil War and the Gettysburg Address. Lincoln is really known for being a great visionary, tremendously strong leader. And you're probably asking yourself, why would we want to talk about Abraham Lincoln in a technology presentation? And the answer is really quite simple. Is that time and time again, when I'm visiting with clients, people will talk about their data in its entirety, and they want to treat their data all the same. And while all men are created equal is true, and just as we run a country, that same premise is not a good idea when we look at how we want to treat our data and how we want to store our data. So earlier in the year, I had the chance to travel to a few cities here, Minneapolis, Salt Lake City, and here in Denver as well. And I gave a presentation on the 7 deadly sins of data protection. Sin number 2 was treat your data equally, right? And so again, as we start to get into this presentation, we're going to look at different types of Flash media that's out there today, what's on the horizon, and how we want to be able to segment the types of data that we have and make sure we assign it to the proper media. So right now, we have this unprecedented, phenomenal growth in data, right? And what's driving that data growth are 3 big components, right? The first one's social media. I'm sure most of us either have a LinkedIn page, right? We have a Facebook account, Twitter account, something like that. And so we're generating this large amount of data at a very rapid rate. We all have mobile devices now. We have a lot of apps on there. These apps are starting to generate, again, a large amount of data. These apps are actually linked to a lot of these social media sites. And then finally, we have the Internet of Things, which is, again, like the cloud, can be a very vague term. But this Internet of Things, particularly machine-generated data, is going to create 90% of all new data that's created each and every year. For example, when we talk about machine-generated data, there are some very exciting things that are going on in the industry in IT, one of which in the retail sector. So if I go out and I take my phone and I load an application from a retail vendor, say like a Walmart or some kind of grocery store, I then go into a retail unit. Suddenly that app can now begin to communicate with transponders in that store. They can track my movement in that store. And as I go down a particular aisle, and maybe I'm going to buy some pickles, via SMS text, suddenly I get a coupon for 50 cents off a jar of pickles, right? So now I'm beginning to be incentivized to start to buy things when I'm at this retail unit. Another explosion that we're seeing, and this one is, Sanity has a chance to work on this, with 2 really primary cable companies, it's Comcast and Time Warner. And what they have designs to do is that what they want to do is they want to look at your set-top box. They want to be able to see in real time what you're viewing on that set-top box. They want to be able to ingest that, analyze it, and then be able to turn that around and target you with specific ads and commercials, right? Now, if you guys are old enough to remember how ratings used to work, right, through the Nielsen system, you would get a phone call from Nielsen. You would agree to do the Nielsen rating for a period of a couple of weeks, right? They would send you a book. You would fill out this book about what you watched and when you watched, and then that information was then submitted back to cable companies, advertisers, and things like that. So imagine, we're taking this process just 10 years ago, right? That was a phone call, it was paper, mailing, things like that, right? And now we've turned it into a real-time event, right? That's pretty exciting. E-commerce, right? This is the final thing that's starting to show some really exciting trends. Now, a lot of us have probably shopped on Amazon and websites similar to that, right? What's the biggest impediment with online shopping? I can't get the product right away, right? Because we're a society that needs to have things immediately. So if you take a look at this slide, look at that lower left-hand corner, right? The ultimate goal here in the supply chain is, for me at home, if I'm in a large metropolitan area in the next couple of years, I can sit down and I can order something, say on an Amazon. That order goes into the supply chain, right? That order then gets picked, invoiced, gets loaded on a drone, and potentially within 30 minutes, that package is at my door, right? Exciting things, and why are we talking about this? Because it's the infrastructure that sits behind all these mechanisms, right? This flash that we will talk about in greater detail is starting to drive all these new trends. And then finally, right, the goal of smart everything, right? We talk about having smart cities, right, where certain portions of the grids can come up and down, right? Street lights can be automated in a more synchronous fashion, things like that, save energy. We talk about smart health. The VA system, for example, is adopting appliances now that they can send home to veterans, where veterans can now get monitoring, some low-level checkup stats on a daily basis, and all this information gets uploaded and transmitted to the VA, goes into a large database, and now the VA can start to monitor people with certain health conditions on a daily basis without deploying any kind of human intervention. And then finally, smart homes, right? We can start to control power consumption, we can control heating and cooling, the way we light our homes. We can do this all in an automated fashion. There's a company just in Boulder called Tendril Networks that is one of the leaders in this industry as well. So we've seen these great trends going on, right? Adding to the convenience of our life, adding to the speed of how we're doing things, giving us new capabilities. And what's driving all that is this whole host of new applications and databases that are being adopted, right? The common thread for all of these apps and databases is just right here, right? In memory. Oracle now supports in-memory. They have for the last couple of years. SQL, its latest release, right? They support in-memory processing. And what you will find out is that if I can start to process data in memory, I can start to do things in real time, and it starts to give me different capabilities that I may not have had as recently as 2 or 3 years ago. So today's business driver, it's really simple, right? It's more data. It's manipulated at a greater rate, right? So I can make decisions a lot faster. That's really the big business driver. When we look at this continuum, right, the last 15 years of time, if you look at the far left of this, in year 2000, we would look at data in historical context, right? We would analyze it, right? And then we moved to the year 2005, and then we'd start to do maybe some modeling of that data, right? The insurance industry was really the first one that jumped on the modeling portion. And then if you go all the way to present day, and the things that we've already talked about is, right, real-time governance, right? Real-time manipulating of the data, so now I can harvest this data, and in most cases, it either, one, it will add to the customer satisfaction or the customer experience, or two, it opens the gates for brand new revenue streams. So here's the question, right? Again, even if I'm an SMB, what do 1,000 more operations mean to me, whether it's per second, per minute, or per day? What does that mean? Right? If I could do 1,000 more operations, does it mean my workforce is happier? They get things done faster? Maybe I can run different types of reports. Maybe I can begin to mine data in my SMB environment. Right? Again, it begins to give me more capability. And here's the most important thing. When you look at this answer is, when you think about solid state, the thing is, this is not about gig or dollar per gig anymore, right? That's the old argument. You need to think about SSD as, what's the capability that it's going to give you? So let's unlock this real-time performance with solid-state technology, right? The definition of solid state, it's really simple, right? It's just non-volatile computer storage chips, right, that we can program in place. Basically, that's all it is. When we look at a small form factor drive, and for the rest of the presentation, keep these components in mind. We have an integrated circuit board. We have the NAND flash chips that are located on that board. To the far left, we have a SATA interface, right? But the two most important components that we've seen the most development from are going to be the controller and the DRAM. And so as we talk about technology, keep those in mind because they're really going to influence what's going on in the market. So the whole reason we've got SSD as this big focal point right now is that we've seen this exponential growth in two things on the compute side, right? Processors, going back to Ivy Bridge, it was a significant release from Intel, right? Suddenly we're into the Haswells, Broadwell is just around the corner. And then next year, we're going to see this huge innovation with Skylake from Intel, right? It's going to be a quantum leap in efficiencies. It's going to be much, much more powerful and use much less energy, right? So we have this dramatic curve of processing capability. When we look at system memory, right? We're now in the 4th generation of system memory. And so again, those capabilities are becoming more powerful and less latent. Well, with the old mechanical drives, they were static. Right? A 15,000 RPM drive was only going to do 200 IOPS, and that's all it was going to do. There was no improvement. And so with the introduction of NAND flash, we can now start to bridge that gap, right, between the chasm of performance of the compute side and the storage side. When we look at the different categories that we're going to be focusing on, right, we've got hybrid arrays, we've got all-flash arrays. We have things like data accelerators. Myself personally, I'm a big fan of data accelerators and server cache because as an SMB, I have a specific depreciation schedule that I have to maintain, right? And if I can be strategic in my allocation of flash, I can elongate that depreciation schedule and get the full use life out of those products. For those of you old enough for Pac-Man, right, the flash market really has become a game of Pac-Man. There has been so much M&A activity, it has been frenetic. We've got the different categories right now. We've got the all-flash array, we have hyperconverged, and then we have the hybrids. But down the bottom, you can start to see all these companies that have been acquired. Texas Memory has been acquired by IBM, right? This is the latest one. I don't know if you guys saw this in the news about 3 weeks ago. SanDisk was consumed by HGST, right? And the big motivation behind that is, as this market gets more competitive, it's very, very important that these companies can fabricate their own name. And so HGST, which was a big player in acceleration products, they did not have that capability. So the reason they bought SanDisk for $19 billion was so they could have that capability to fabricate, or in the industry is what they call a fab. As we look at these categories, though, we've got a couple of local representatives. SolidFire and Pure Storage have both done very well in this space. And the thing is, what you're going to see with these new generations of products is that they're giving you new capabilities, right? And so they're going to be able to do both types of data reduction in the form of deduplication and compression. SolidFire has a great feature where they can assign quality of service now to each individual client. And so these new capabilities are things that we haven't seen before. And then, of course, that's all in addition to the low rate, high performance that you're going to get that is just endeared to SSD drives typically. On the hybrid array side, the two big players that we see quite a bit are Tegile and Nimble. And then finally, with the hyper-converged, right? Hyper-converged meaning I've got compute, storage, and networking all in a single device. The big one out of this group that we see that's really come to the forefront is Nutanix. So we look at IDC's chart for decreasing prices, right? And so the biggest impediment to the adoption of solid state has always been price, because again, people look at this as dollar per gig, right? And as we mentioned earlier, that's really the wrong way to look at the capabilities of SSD. But the top three lines, the blue line represents single level cell. The next line, the red line, is we're looking at multi-level, and then the green is TLC, or triple level. And so TLC has really made some big inroads this year. Dell Compellent recently announced that they were going to start using it in their enterprise storage arrays. And so they're going to be the first adopter of TLC, which again, we were very excited to see this happen. And as we get deeper into the presentation, we'll talk about the reasons for that. And what you can see with TLC is nearly the same cost as 15,000 RPM disk drives. One of my favorites here, my colleague Mike Luck, sitting over in the back here, who was a great contributor to this presentation. We have wrestled around with a way to talk about latency, right, and how to explain latency. And so I got this idea from an Intel presentation that I saw last week in Florida. And so if storage devices were sprinters, right, a 15,000 RPM drive can sprint 94 feet the length of a basketball court. Well, if that sprinter was NAND flash, look what it could do in that same period of time. It could run a marathon. And just in September, Intel and Micron jointly announced an exciting new product that we'll talk about, 3D Crosspoint. And look at the capabilities there. Crosspoint, in the time that a hard drive could run 94 feet, right, it could circumnavigate the globe. To me, that's really a tremendous wow factor, very impressive. So this aha moment that we have is, right, we talk about IOPS and speed, right, but really the other part of this equation is going to be latency. And as we just saw with our chart before this, right, that low late behavior can really make a dramatic difference on our infrastructure. One more way to look at this, if we were to take functions within the server stack, right, and we just assign an arbitrary number to it. For example, if we do a compute I/O, right, which again, 0.3 of a nanosecond, let's say we just throw an arbitrary time of 1 second. Now I ask you to go down the chart and take a look at main memory, right, which is DRAM. Right? So the latent behavior associated between I/O going through the processor and DRAM, right? Look at that, 1 second to 6 minutes. And if we were to look at the rotational disk drive, that same I/O would take 4 to 12 months. Right? Again, these are just arbitrary numbers trying to explain to you the value of low latent behavior within your architecture. So what's your game plan? Well, we want to identify the bottleneck in an application, right? So if we have this application, and maybe it's our main money maker, maybe it's the one that really drives our business, if we're having issues with it, it's not performing quite well, we want to identify that. We want to analyze the way that code is written, and we want to analyze the physical hardware that application is sitting on. And then we want to ask ourselves, is this a global opportunity, or is it more of a strategic opportunity? And that's a very good question to ask, because it can save you a lot of money. And I'll give you a quick example of this. I was working with a client recently. He came to me and he said, well, we just acquired another company. We're ingesting all of their data. Suddenly now we've hit this bottleneck. We're having a global issue with I/O constraint. So we went in and we analyzed the situation that was going on. And the caveat to all this was they had just purchased a new storage array the previous year, so they didn't have budget to buy another one or expand this. And so we went in and we analyzed the situation. What we found out was that there were several SQL databases that were the largest consumers of I/O. So by simply taking a form of solid state, in this case it was PCIe flash cards, we installed those in a few servers. We offloaded simply just the 10 DB, which was the biggest consumer of all of I/O. And now we were able to free up the storage array to be able to service I/O and the rest of the organization. And 10 months later, they're still fine. So it was a very cost-effective way. So again, as you analyze your own environment, right, not every issue or every situation you run into is going to be addressed maybe globally. There could be very strategic opportunities for you. So let's look at SSD a little bit closer, right? The big thing is we don't have mechanical barriers, right? We no longer experience rotational latencies, or we don't experience sleep latencies. We have traditional form factors, right? Typically 2.5 inch. If you have older servers and you want to retrofit those with an SSD drive, all SSD drives today are 2.5 inch, but companies do use 3.5 inch drive carriers for those. So they will fit older servers if you have it. We're starting to see a huge increase in 1.8 inch drives. And then right here, M.2, in memory. It's an actual drive that's plugging into the memory bus. Exactly. Somebody just raised their eyebrows. Exactly. And you're going to see when we talk about the Intel announcement, it's going to play perfect into that memory bus. So here's some terms that you need to be familiar with. Right? Drive writes per day. There's a way that we measure endurance on an SSD drive, and one of them is DWDP. And so basically what that means, I'll give you an example. If I have an 800 gig drive, that drive is going to be given a DWDP of, say, for example, I can fill this drive up 8 times a day, 7 days a week, 52 weeks out of the year, over 5 years. Doesn't matter what size that drive is, that's the DWDP. More commonly, what we're starting to see now is just simply terabytes written. Particularly like with a single level cell drive, which is the most enduring, we will see that total terabytes written into petabytes. Could be as high as 20 petabytes per single drive. When we start to move down the food chain into, say, multi-level or triple-level cell, those numbers will begin to fall substantially, right? And it could be into the terabytes for the lifetime of that drive. So when you're working on the right solution, right, here are your choices. You want to do like a standard or small form factor drive. You want to do a bus-based solid state, right? And when Mike and I wrote this last year, that middle arrow said PCI bus, and now this year with M.2, it's just bus-based. Or do you want a global solid state solution, right? So let's talk about our choices here, right? Single level cell, right? We've got 1 bit in every cell. And what do we know about single level cell? It's the most enduring, it's the fastest drive, and it's the most expensive drive, right? And they typically come in the smallest sizes. The answer to the single level cell, which was the first type of drive that was introduced into the enterprise, was the multi-level cell drive, right? And now we start putting 2 bits into every cell. And so with the MLC drives, there's just a MLC or an eMLC. And believe it or not, the enterprise version is actually slower than just the regular MLC. And the reason it is if you guys think back now to our diagram of a small form factor drive that was exploded, right? We have that DRAM chip that sits on the integrated circuit board. MLC drives, the enterprise version, they do write buffering, right? So they're going to buffer everything to DRAM, and then they're going to do what we call wide striping or write coalescing out to all the individual cells underneath. But with the MLC drives, what we see is greater capacity. They're going to be a little bit slower, but they're going to cost a lot less money, right? And again, endurance is going to be somewhat less. And then we get into the triple level cell, which is just 2015 is really making its way into the enterprise. And to us, it's very exciting. But the triple level cell is going to have 3 bits in every cell. Right? It's going to be even less endurant than the MLC drives. It's going to be much larger in capacity, and we'll talk about those a little bit later. But again, the endurance level goes way down. And so when we talk about terabytes written per drive, these drives could be as little as 20 or 30 terabytes. Right? But if we position those in our enterprise in the right way and at the right level, primarily what we call like maybe a read-only device, those drives can last an extremely long period of time. Now, what we know about endurance is writes and deletes affect endurance. So there's a couple other behavior patterns that go on inside solid state that you may not be aware of. One of them is write amplification. So within the cells of the SSD, what happens is we're going to write at the page level, 4K page level. But I have to delete at a block level, right? And so the block level is actually an aggregation of pages. So in this example, if I start out with blocks A through F, but now I want to modify A through C with A prime, B prime, and C prime. So what happens is I have to then copy D, E, and F, A prime, B prime, and C prime over to a new block, right? I have to copy those over, so now I'm rewriting the data, and then I have to go back and erase the original block, right? So now I've written the data a couple times, right? And that's what's referred to as write amplification. So every time I do any kind of delete or write, I have this other activity that goes on in the background. When you're in a situation where you have this repeated just write-delete process that's just cycling at a very tremendously high rate, we don't see this in the SMB space, but at a large enterprise we will see it. It's referred to as a write cliff. And what will happen is the drive will actually start to tank performance, right? And that write cliff happens. Another key phrase that you should be aware of is called wear level, right? The second biggest concern with SSD drives is always about, boy, I'm afraid this thing's not going to last, right? And there's concerns about endurance. So what happens is, going back to that image of the exploded drive, we look at that controller, and that controller is going to have a lookup table on it. It's going to use an algorithm. And if we go back to our first slide about Abraham Lincoln, right? Well, that lookup table, that algorithm says, you know what? All my cells are created equally, and I want to use each one the same amount of time, right? And so what happens is each individual cell will be read to exactly the same amount of time. So that distributes the wear over the drive, and again, it enhances the endurance of the drive. The PCIe Magic Bus. Yeah, we're all big fans of the PCI cards because, again, it's a very strategic opportunity to use flash. Now, one of the things that we've seen happen in the last 12 months is that the software for these products has really gotten very advanced. I'm going to give you an example. SanDisk makes a product called DASCache. I simply load this onto a server, and now I can take a PCIe card and turn it into a read-write caching area for my server. I can use that in databases. I can use that in a virtual infrastructure. And suddenly now, all of my real-time transactions can happen on a PCI card, right? Which makes a tremendous amount of improvement in performance. And again, this third point here is another great point, is that it's all about location where I put SSD. The closer I can get to the processor, right, the lower the latency I have. And once I get away from the standard form factor drives, I no longer deal with the SCSI protocol. Right? So I have a shorter protocol stack, shorter distance to the processor. So let's look at some of these key features. I have the capability, in some cases, to do 500,000, 700,000 IOPS on a single card. I mean, it's just phenomenal the capabilities that I have, right? And again, and even in a 30 or 7 to 30 read write, I can still do 400,000 IOP in third generation cards. Think about what that would take if you had 15,000 RPM drive, right, that would do 200 IOPS each. So pretty substantial increase there. So application metrics, right? So when you're thinking about this type of flash within your environment, right, where am I going to use it and how am I going to use it, right? Am I going to use it for transactional? Am I going to use it for random? And what about the block size, right? That block size is really, really critical question to ask yourself. Because what happens is, with SSD, that has to go through the SCSI protocol stack. If you have an unusually large block size, it's going to really bog things down. So let's talk about some emerging technology that's going on in the market today, right? So today, the primary NAND flash that we see is 2D NAND. That is slowly being replaced by 3D NAND. Google is leading the way with that as far as being an early adopter of 3D NAND. And so all the big companies like Samsung and Intel are fabricating 3D NAND in full force now. And basically, if you look at this structure, you can see that the NAND cells are actually going vertical and they're interlocking, which is really important to consider as we look at newer generations that come out beyond that. If we look at it a little bit closer, in the upper left-hand corner, that's a 2D NAND cell string. And so in 3D, what we've done is we take the middle, we stretch it out, we bend it to a horseshoe shape, right, and then we stand it up. So now we're building vertically, right, instead of linearly, and then we can actually interlock these components. And so the obvious that you can see from this is we get tremendously more density. And what's interesting, SanDisk came out with this slide recently, and they're talking about the different changes like in mechanical drives. And for example, like say 10,000 RPM drives, we've seen those drives go from 900 gig to 1.2 terabyte to 1.6 terabyte. During that same period of time, we're seeing 2.5-inch SSDs go from 4 to 8 to 16 terabyte size. Server SANs. Fascinating technology here. So what happens here is that I use PCIe flash cards, and I use a dedicated network. It could be 10 gig, it could be 25 gig, it could be 40 gig, right? It could be RDMA. But I put flash cards in the servers. I use cache coherent software, and suddenly now, like say if I have an Oracle rack, maybe some really heavy SQL processing going on, I can now create a dedicated SAN for that process that can generate over 1 million IOPS. It's also extremely low latency data. So when we look at this, and we've talked about our technology, right? On the right-hand side, we have volatile memory, right? Because we have memory on the computer chip, we have the DRAM. On the far left, we have mechanical drives, we have the SAS drives, right? We have PCI, but there's something missing, right? There's something missing in that chasm. And what that is, it's the 3D crosspoint, right? This was just simply announced back in September. Fascinating technology, and it really bridges that gap between non-volatile and high-performance media. I'll let you guys read this. The bold I thought was really funny, but it's a great way to describe 3D crosspoint. This is from Dave Altavilla from Forbes magazine, in describing the announcement of 3D crosspoint, right? Absolute thermal nuclear detonation. That is how much different 3D crosspoint is and will be to the market in the coming years. When we look at it, right, again, look at that. It's stackable and vertical, just like we saw in 3D NAND. So now we're talking very high densities. What we think, because this hasn't been announced yet, but what we think is this product, this is phase change memory. So if you remember earlier, we talked about floating gates, trapping charges with 2D and 3D NAND. That all goes away. We're going to be changing the phase of a material called chalcogenide, right? And so what happens is, because we're only changing the phase, it's lower latent, higher performance, and any concerns of latency now go out the window. And so where 3D crosspoint fits in, right? It fits in nicely between this capability, right, of say PCI cards and DRAM. And it's going to offer much greater capacities than what we have with DRAM. It's going to offer comparable performance of DRAM. And once again, we're not going to have any concerns about any kind of endurance problems with this type of storage. Right? And then so finally for your consideration, right? When you look at your own environments, think about application demands, right? Where could I take advantage of solid state technology? What are the performance requirements, right? Understand that different types of NAND has different types of endurance capabilities, right? And based off of that, different price points, right? And different capacities. So when you look at your own environment, think about where this use of NAND is going to go. We have server-side cache out there, right? A very effective tool for high-performance, low-latent opportunities. Compression and deduplication, right? If I can compress the data and dedupe it, suddenly now that physical solid-state space logically becomes much larger, thus makes it much more affordable. Right? And remember the business value. I can't preach this enough. It is not going to be about price per gig anymore. It's about what kind of capabilities does it give my organization. And that's it. If you guys have any questions or want to talk about this at all, I will be available afterwards. So thank you for your time.